In this module, we are going to be looking at discrete functions. So we will start with looking at sequences, which is a list of ordered pairs where each number in that sequence is called a term. Sometimes there is a pattern and sometimes there's not. So we'll look at specific patterns. Sometimes we will have a set of numbers or sequence of numbers where we can easily identify the pattern, and sometimes we won't be able to. So a sequence can be described as t to the 1, t to the 2, t to the 3, and so on to t to the n. So what that means is, let's say we had t to the 5. That means that t to the 5 is the 5th term in that sequence. T to the 10 would be the 10th term in that sequence. And so the subscript has to be a natural number because we are only using whole numbers that are positive. So we're not using 0. So for example, think about it as if you were standing in line and you were describing your position. So this n, or this subscript, describes your position in that line. So you could not be 1.5 position in the line. You couldn't be 3/4 of a position. You couldn't be a negative position. You couldn't even be 0, right? So the first person in the line is position 1. The second person in the line is position 2, and so on. If a sequence is finite, that means that there's an end. If there is no end, it's infinite. So you would see these 3 little dots, which is ellipsis, and that shows you that it continues on forever, whereas in this sequence here, it's finite because you don't see those 3 little dots. So that means that it's a specific end to that sequence. So that's just a little bit of vocabulary. So a lot of sequences have a pattern. As I said, sometimes they do, sometimes they don't. But if it does have a pattern, we can usually describe the sequence by a rule. So we have a rule that describes the pattern, and that rule we'll call the general term. So for example, we want to see if we could find the next 4 terms in the sequence. So in part A, we have the sequence of numbers 17, 22, 27, and 32. And we want to see if we can find some sort of pattern that we could then continue. So I can see that 17 to 22, I am adding 5. So let's see if that pattern continues. So if I add 5 to 22, I get 27. If I add 5 to 27, I get 32. So there is a pattern. The pattern is it's increasing by 5. So then I could add 5 to get the next term. I could add 5 to get the next term. So it wants me to get the next 4 terms. So I'll just keep adding 5 till I get those next 4 terms. In this sequence, this is the points in a football game from the Hamilton Tiger Cats. So in the first game, they get 13 points. The next game they got 21 points, the next game they got 35 points, and then the 4th game they got 17. Well, in a situation like this, there is no pattern because the number of points the team gets in a game is totally random. We don't know how many points they're going to get. There's not going to be a pattern. So we would say there's no pattern, so we can't predict what the next number would be in the next game. The first example was number of seats in a row in an auditorium. So if you think of a row having this number of seats, the next row has this number, the next row has this number. So we can easily find that pattern. And then the third example, they give you a formula. So they give you a general term. So we could just find the next 4 terms in that sequence by just putting in a value for n. So if I want the first term, t to the 1, I just put in a 1 where I see the n. Oops. So it's squared and then minus 4. So if I do that calculation, that works out to be minus 1. And then I could find the second term by putting in a 2. Do that calculation, I could find the third term by putting in a 3. and then I could find the fourth term by putting in a 4. So it's pretty easy to continue the pattern just by substituting it into that general form, term or formula. Okay, so there are specific types of sequences. So the first type we look at is an arithmetic sequence. So in this example, Carolyn is been given $1,000 and she's going to earn simple interest. So what simple interest means is she's getting the same amount every time. So she's getting $1,000 and she's getting 4% every year. So that works out to be $40. So every year she's getting $40. So after the first year she's got $1,040. Second year she gets another $40, so $1,080. The third year she gets another $40. So that would be $1,120. Then she gets another $40. And then she gets another $40. So every year she's getting $40. So we want to see if we could figure out a formula for this sequence. So what we can do is we said, well, she started out with $1,000, and then each year we're adding $40. But we're going to write n minus 1 because we already have the first $40 here. So for example, if I said n equals 0, which is the initial amount, and I put in 0 minus 1, oops, sorry, let's change that. We'll do t to the 1. So after the first year, she's got 1 minus 1 is 0. So at the beginning, she's got $1,000. Then we have 1,000 plus 1 times 40. So now we're at 1,040. So the table here, year 0 would be the beginning. That would be your $1,000. After year 1, it's 1,040 and so on. So we can make a general formula. So we can say we started with an initial amount and then we added the common difference, n minus 1 times, because we have to take into consideration that first amount. So this is your initial amount. This is your common difference. And this is the number of times we're going to do that. So this is the general term for an arithmetic sequence. So A is the initial amount. That's what we're starting with. D is the common difference. So for example, in the first question it says, identify which sequences are arithmetic, and if it is, find the common difference and the general term. So what we can see is in the sequence, does it go up or down by the same amount? So if I go from -9 to -6, I am increasing by 3. If I go from -6 to -3, I am increasing by 3 and 3. The other way to do it is to take, if you're not sure, you can take the second term and subtract the term before it. So -6 plus 9 is 3. And then we can take the third term and subtract the term before it, right? The term preceding it. So we're finding that difference. So -3 plus 6 is also 3. So the common difference is 3. And then we can find the general term. So I'm just going to erase this to give myself some room. Okay, so once I know the common difference, I know the first term is -9, and the common difference is 3. And then we're just going to simplify that by expanding brackets and then collecting like terms. So this is my general formula for that. In the next example, let's make this a bit bigger here. So the first two, I'm increasing by 11. I'm increasing by 22, and I'm increasing by 44. So this is not arithmetic because we are not increasing by the same amount. There is no common difference. Note that there is a pattern. If someone asked me to continue that sequence, I could, because I noticed there is a pattern. I see that we're doubling, right? 11 times 2 is 22, times 2 is 44, times 2 is 88. So I could continue the pattern if I wanted to, if I was asked to. So I would double 88, and I would double 352, and so on. So it's not arithmetic, but there is a pattern. But the question asks, is it arithmetic? And it's not, so we're finished with that question. Okay, question 2 wants us to find the 25th term. So I don't really want to write out 25 numbers. That's kind of tedious and time consuming. So what I'm going to try and do is find the formula, and then I'll just put in 25. So I can see that it's going up by 7, up by 7, up by 7, or again, if you wanted to subtract, take one term, subtract the term before it, do that a couple of times. So -3, subtract -10, and just make sure that there's that common difference. So you can either eyeball it or you can subtract a term by the number before it. So the common difference is 7. The first term is -17. And the general term is -17 plus n minus 1, common difference of 7. So we're just going to simplify this. That works out to be -24. So this is my general term. And once I know the general term, I can just find the 25th term. So that's much more efficient than writing out 7 or 25 numbers. Okay, and generally when the question is asked, they'll ask you to find the general term, so it's a good habit to be able to do that. Okay, in this last example, it wants us to find the 100th term. So what the question says is they've given us 2 terms in the sequence. They've given us the 7th term, that's 53, and they've given us the 11th term, which is 97. We don't know what the first term is, and we don't know what the common difference is. It does tell us it's arithmetic. So we don't know A and we don't know D. But we know T to the 7 is 53, the 7th term. And we know T to the 11 is 97. So if we put those values into our general term, we don't know A. We know that the 7th term, we don't know D, is 53. So we can simplify this. 7 minus 1 is 6. We can do that with the 11th term. We know the 11th term is 97. We don't know A. We know it's the 11th term. And we don't know D. So that'll be A plus 10D. So if you remember from grade 10 math, we can solve this system because we have 2 equations and 2 unknowns. We can solve by either elimination or substitution. I prefer an elimination. It's nicely set up for that. You can do substitution if you want. That's up to you. Whatever method you are comfortable with. But I'm just going to subtract these 2 equations because if I subtract, I see that the A's would add to 0. So I'll do 97 minus 53 is 44. The A's add to 0. And then 10 minus 6 is 4. And then we'll divide by 4 to solve for D. So the difference is 11. Once we know the difference, we can go back and find A using either equation. Doesn't really matter which one. And so A is going to work out to be -19. So once we know A and we know D, we can write the general term. So the first term is -19. The common difference is 11. And then we'll just expand and collect like terms. So 11n minus 130 is my general term. And then remember the question asks for the 100th term. So we'll just put in 100. And that works out to be 970.